Hello, and welcome to part 2 of worksheet number 6. Now, you may have just watched my last video and thought, wow, that was a really long video, and that problem was a lot more complicated than I thought it was going to be, and there was some weird runtime stuff at the end. Wow, they have to go easier on us for the next part of the worksheet. Well, unfortunately, you're wrong. I think that this part of the worksheet, in particular problem 2b, is probably the hardest problem we do on any of the worksheets in 621b. It's all about runtime. It's all about the nuances of runtime. And these are things which are very, very confusing to new students. They're things which are very confusing to returning TAs. So I'm going to try to explain this in the best way I can. I'll give you some rationale of how to compare different runtimes, what O, omega, and theta actually mean. And yeah, just teach you how to address some of these things and hopefully make sure that you're using the correct terminology, because that's something that's also really easy to mess up. Okay, before we get there though, we're basically introducing you to the different runtimes in problem 2a. We're just telling you to put these in order. I'm not going to spend a lot of time on this. I'm just going to tell you the order. This is an order that you will end up memorizing pretty easily. It's something that comes up a lot, but basically here's the order. It's going to be constant time, then log n, then O of n, then O of n log n, O of n squared log n, and then the really bad ones, O of, well, oops, that's supposed to be O of n to the third, O of to the n, O of n factorial, and O of n to the n. Okay, what do these individual runtimes mean? These basically refer to the amount of time it takes a particular operation to complete based off its input. Now, runtime is a bit of a misnomer. It isn't necessarily the case that a function that runs in n log n is always going to run faster than a function that runs in constant time or O of 1. That's not what we're saying. What we're saying is, as the input to a given function, described this way, increases, it's going to increase at a faster rate than this particular function, right? But yeah, so these are the main ones you're going to have to work with. In particular, you should probably look out for constant time, log n, n log n. One that's not on here is n squared. And then these ones don't really worry about. For the most part, these are really, really bad runtimes. They're just for the sake of demonstration. And I'm not even going to spend a lot of time talking about these because you'll memorize them. You'll get to know them very intimately as we do more data structures. It's more worth it for me to focus on 2b right here. But that's basically how this works. Okay, so let's talk a little bit about runtime before we actually address this problem, because you might look at this problem and have no idea what it even wants you to do. So basically, it's asking you if these statements are true or false. If they are false, you should correct them. Another thing to note here is we are always looking for the tightest bound, but you might not even know what this is asking, what this notation means, what a tightest bound is. Okay, so what we're doing is we're talking about runtime here, right? And I think the easiest way to try to understand runtime is to look at it graphically. So we have three terms here, O, theta, and omega, and they all mean something graphically. So O is an upper bound, theta is a tight bound, whoops, and omega is a lower bound. Again, terms that might not even mean anything to you yet. What do they mean? These are all referencing how long, again, a given function takes based on its input size. So imagine an array, and let's say the array has some elements in it, and I don't really care what they are. And let's say you want to scan through this entire array, and you just want to print out every element. Well, how long does it take to do that? Well, obviously the amount of time that it takes to do that is proportional to how big the array is, right? The bigger the array, the longer it's going to take. And in particular, if the array is of length n, just say there are n elements in it, well, you're going to have to go through and you're going to have to print n things. So we'd say that this operation takes n time, right? That's the basic understanding of it, right? So as the array gets bigger, the time gets bigger. And we can represent that graphically as well. So let's say you have a graph here, and here is time to complete, and here is input size. So if something is linear, right, it's going to look like this. It's going to be a graph like this, right? And this is what we were just doing with our array. So let's say that we have an array that is size 5. How long is it going to take to print everything out? It's going to take 5 units of time, right? If it's size 10, how long is it going to take to print everything out? 10 units of time, right? So you see we have this linear line. That's why it's called linear time, right? In other words, as the input size increases, so too does the time to complete the operation in a linear fashion, right? And this is n. Other runtimes are going to look different. So imagine n squared, right? Something like n squared is going to look more like this, right? This is just recalling, what a graph looks like if you graph it on a graphing calculator, right? Something like n squared is going to do this. So if you imagine an operation that takes n squared, that might mean that if the input is of size 3, it's going to take 9 kind of units of time to finish an operation. If the input is of size 10, it's going to take 100 units, right? You can see here that we take more and more time the bigger the input is, and it's not strictly linear, right? The amount increases, we go up. So it might look like this. The opposite of that might be like a log n time. So imagine we had log n now. The log graph generally looks like this. It starts out fairly steep, pretty much linear, and then it's going to quickly decay. It's going to keep increasing forever, but it's going to increase at a decaying rate, right? This means that the bigger a particular operation gets, the less time it's going to take actually to complete that operation. This is very common in trees and binary searches and stuff like that. Again, I'm strictly staying to the kind of conceptual high level, but as we look at trees and other data structures, you'll get a lot of examples of log time, right? Okay, great. So that's some different, numbers. But where do these things come in? Whoops. Where does this O and theta and omega come in? Well, let's look at O and theta first. So let's go back to having a log function. This is log n, right? It's just a line. Okay. So if we describe a function as O of log n, right, that means that log n is the upper bound on that function, meaning that the function can take no longer than O of n time, right? So in other words, if this is O(n), this line I just drew, this is the upper bound, which means that our function can exist anywhere here, anywhere in this lower bound, the shaded area. Conversely, omega is the lower bound. So if we have a function that is omega of log n, that means it must take at least n time to complete. So it would be anything shaded up here. Okay. So now let's look into another example, right? So here we have this omega of n, of log n. Now let's think back to this array example I was talking about previously. In the array example, where you're just going through an array and you're printing through every element, that is going to take n time. So in other words, it's going to look something like this. Oops, it looks a little bendy. But it's going to look something like this, right? It's going to be linear. It's going to be sharper, at a sharper incline than log n, because remember, log n is going to decrease its slope as it goes on, but linear is not going to, right? Okay, so now we can start making statements here. We know that the array iteration is going to take n. It's actually going to take theta n. Don't worry about the theta for now, but it's going to take theta n. So now here's a statement I want to ask you. It's basically, what is the relationship between these two based on the picture, right? And we can start putting these relationships into concrete terms. So we use the set theory notation. This means in. And we're able to say something like this, that theta n is in omega log n, right? What that means is that the runtime of this function is contained within the runtime of this function. And graphically, we can see this, right? Because the black shaded area, that is omega log n, right? It is at that line or above that line. So that, shaded area extends up infinitely. And what we can see is that we see that the n, that theta n, is completely contained within that shaded region. Therefore, it's fair for us to say that O of n is contained within omega log n. Okay, let's look at another example with some similar logic. Ugh, I'm so bad at drawing graphs. Here, I'm going to zoom all the way in. So, okay, another example. Same thing here, but now what we're going to be doing is we're going to be comparing two omegas. We're going to be comparing omega n and omega n squared. And let's make them different colors too, so that everything is really clear and easy to see. Omega n, let's go with red, omega n squared. Okay, we know that omega n squared is bigger than omega n, right? So let's just pick one to draw first. what is omega n squared? Well, n squared looks generally something like this, right? And omega is an upper bound, meaning that everything below this line is going to be within O of n squared. So you just kind of draw this shaded area in. You can imagine the shaded area extends out infinitely that way, infinitely up, right? It's just everything under the line. Okay, now let's draw O of n, right? So O again is an upper bound. So it means we're going to draw a line and we're going to shade everything below the line. Okay. So now here's my question to you. Is this statement true? In other words, is the area shaded in the blue, O of n, is it contained completely within the area shaded in n squared? And the answer here is actually yes. Now, you might say, wait a second, right? I see this little area down here, right? There's a little area where n is actually bigger than n squared, right? And this is the area of like decimals, right? You can imagine, for example, 0.5 is bigger than 0.5 squared, right? Once you get to 1, n squared is going to dominate, but before that, it's the other way around. Another thing that's very important about runtime is we only care about numbers as they go to infinity, basically. That's another thing you're going to hear a lot, as n goes to infinity. So basically what I'm asking is, as n goes into infinity, how do these two things grow? We know that something that's linear is going to grow in a straight line. It's going to continue on, and something that's n squared is going to grow up at an ever increasing angle, right? Basically, in short, don't worry about this little part at the beginning. We only care about numbers as they get bigger. And one thing that you'll see is that as n and n squared get bigger, this blue shaded region is completely contained within the red shaded region, which means it's fair to say that O of n is contained within O of n squared. Okay? Here's a question. Is this true? Right? Is it true that O of n squared is contained within O of n? Well, it's not, right? Because what is O of n? O of n is the blue shaded region. O of n squared is the red shaded region. The red shaded region is partially, but not completely, contained within the blue region. But because it's not completely contained within the blue region, we cannot say, this statement is not true, right? Okay. Let's look at a couple other quick examples just to really kind of pin this down and illustrate this. Get ready. I'm going to come up with some more examples off the top of my head. So let's do an omega bound. Let's do an omega of n squared, and let's do an O of log n. Okay, log n looks like this. O means everything at or below the line. Omega is going to be n squared, which looks generally like this, and omega means everything at or above the line. Okay, so here's some statements. Is this true? The answer is no, because again, the blue shaded region is not contained completely within the red shaded region. Is this true? Again, the answer is no, because the red shaded region is not contained completely within the blue region. There might be a little bit of overlap here in very small numbers, but we don't really care about that overlap. We're only looking about as things go to infinity, right? In other words, you can imagine the tip of this arrow, as the red tip of this arrow continues on, will it always be in the blue shaded region? In this case, it will not be. A couple more quick points to illustrate. There's some confusion about what omega of 1 means. Is a really common thing. And let's think about it with the same approach we were just taking before. Omega 1, okay, constant. What does constant mean? It means that the runtime is like this, right? It just goes on forever, right? At one point. And omega means at or above the line. So it's basically this shaded region. Okay, now again, what does omega mean? Omega is a lower bound. It means this particular function takes at least this operation. Constant time is 1. So in other words, you're saying this operation takes at least constant time, which if you think about it is kind of a meaningless statement because any operation takes constant time, right? Any operation that happens takes some amount of time. So it's fair to call pretty much any operation in omega 1. So let's consider now omega n is going to look like this, right? is it fair to say that omega n is in omega 1? And it is, because again, remember, we can think of it a bunch of different ways, right? First of all, we can think of it that this is saying constant time. We're saying, is linear time contained within constant time? It is, because anything that takes linear time takes at least constant time. So we can think of it logically. We can also think of it pictorially here, because we have the red shaded region, we see the blue shaded region. The red shaded region is completely contained within the blue shaded region. Again, there's a little bit here where it's not, but we don't care about very small numbers. What really matters is that the tip of this arrow, as it continues going on, is always going to be within the blue shaded region. Okay, well, something you might say is, well, okay, I drew the blue arrow there, but what if the blue arrow was up here? It doesn't matter, because the red arrow is still eventually going to be within the blue arrow. What if the blue arrow is all the way down here? It doesn't matter, right? Because any amount of constant time is not going to grow at all. It's going to stay the same. And any amount of linear time is always going to grow at the same rate. So the red arrow, because it is angled upwards, is always going to eventually come into an area where there's blue arrow. You can imagine if, I had this diagram and 10 miles above, the blue arrow was up here, this statement would still be true, because eventually this red arrow is still going to get into that blue shaded region. That's another reason why you may have seen people say things like, oh, if something takes, O of 1,000 time, it actually takes O of 1 time. That's exactly what we're doing right here, right? We're taking away constant factors, right? And on another note about constant factors, let's consider something else again. Let's now look at O of n and O of n squared. I think we may have done this one before, but I'm going to do it again in terms of constant factors. Let's say it's, an O of n squared. What is O of n squared? O of n squared, hopefully you're comfortable at this point, is something like this, and the shaded region under that, to make that a little bit cleaner. And O of n is basically linear. The linear shaded region underneath this area might be exposed, but don't worry, it's fair to say that this is contained within this. Okay, sure. Let's look at some constant factors now. Okay, let's say we were doing O of 2n, right? Well, if this is O of n, O of 2n would still be a line because it's still linear. But if this is O of n, O of 2n might look like this, like a line but at a steeper angle. Let's consider O of 20n. It might look something like this, like even steeper. And of course, imagine that this whole area is shaded below. Okay, notice though that because something that is linear always increases at the same rate, and something that is n squared is always increasing its rate of ascent, that eventually, no matter how big we make the constant factor, whether we say 2 million n or whatever, eventually this blue arrow, as it extends, is going to end up completely contained forevermore within the region dominated by the red highlight. That's why we can get rid of constant terms. Great. Okay. I think we spent enough time on this, and I hope this makes some sense to you. If it doesn't, don't worry, this is like the hardest part of the class. Okay, so we were addressing O and we were addressing omega, but we haven't actually talked about theta yet. So what is theta? Theta is what you use when the O and the N are the same. So O is the upper bound, right? It means that we are at the line or below. Omega is the lower bound. It means we're at the line or above. So imagine this. Imagine a situation where both these things are true. Imagine, in other words, something like this, where we have O of n and we have omega of n. Okay, what does O of n look like? O of n looks like this, at or below this line. And omega n looks like this. It's the same, it's the same line. Try to imagine it's the same, and it means at or above the line. Okay, so here's my question. What is the only region? There's only one place, where these two regions, the red and the blue region, intersect. And it's at the line itself, right? The only place where it is true that you are both in the blue region and at the red region is this line. When we have this case, we describe this line as theta n. That's what it means to be both upper bounded and lower bounded by the same thing. This is also why you'll hear people say you can only have a theta bound when the omega bound and the O bound are the same, because this is what it means, right? So in other words, if we want to draw an omega bound in the same way that we were drawing the other bounds, we would draw it the same way. We just wouldn't draw any shading above or below. So here's a statement for you. let's say that we have a green omega. Oh, okay. Oh, my color. Let's say we have omega n, and we want to ask the question, is omega n, sorry about that, geez, is omega n in O of n squared? Okay, what is O of n squared? Drawn it several times before at this point, looks something like this. What is O of n? O of n is linear, looks generally like this. And remember, because we are both upper bounded and lower bounded by n, there's no shading, it's only the line itself. But the question is still the same. The question is this thing, the region described by this thing, completely contained within the region described by this thing? And the answer in this case is yes, right? We see that O of n is in O squared of n because O squared, or O of n squared refers to this entire shaded region below, and O of n refers to just the line, right? This statement here would also be true if we just said that O of n is within O of n squared, because again, now O of n would refer to this line and everything shaded below, right? It refers to only more. Okay. Here's another question though. Could we say something like this, where could we say O of n is contained within, or sorry, theta n is contained within theta n squared? And the answer is no, this is not correct. Because look, we're basically again asking, is the green region contained completely within the red region? Well, the red region is now literally only this line, right? So it's not any shading. So the green region we see is not going to eventually be contained completely within the red region, therefore the statement is false. However, you can say something like this, because if this is the case, right, both these lines are going to be the same thing, and they're going to be contained within each other. Okay, I hope that makes sense. That is basically my big explanation on asymptotics and running time. Now let's actually do this problem now that I've given you this huge explanation. And don't worry, we will justify it the same way with drawing, with diagrams. But yeah, so, okay. So what we're saying is, are these statements here, which hopefully, after going through that explanation, we now know how to read, are these statements true or false? And keep in mind, if they're not giving the tightest bound, they are false. What does the tightest bound mean? Well, sorry, I actually do have to draw another picture again. Okay, so remember, it was fair to say something along the lines of theta n is contained within omega, omega 1, because omega 1 just is this entire line, right? It basically means anything, and theta n is here. So this is a true statement. This is not a tight bound though, right? It's not a very useful statement either, because again, remember, omega 1 basically means it takes some amount of runtime, right? It takes some runtime is all it means. That's not a very helpful statement, right? It would be more accurate to say something like omega of n, omega of n, because then omega n wouldn't be this blue line, it would be this blue line, right? See how it's closer to describing the actual green line, but it doesn't quite describe it entirely yet, because now we've eliminated all this unnecessary stuff below, right, n, but we still have this unnecessary stuff above n. So it's still not a tight bound, right? So in the end, really the only way to describe a tight bound with a theta would be something like this, because this would be the tight bound, okay? I hope that makes some sense. If not, we're gonna do the actual problems. Hopefully they'll make some sense there. Okay, let's do the problems. So each of these problems is going to have two steps. The first thing is we need to simplify the expression. We need to remove any constant factors. And then once we actually have those, then we can plot them and we can see if the statement is true or false. And there's actually three steps. On the third statement, the third step is to correct it if it's wrong. Okay, great. Now that I've done this introduction for like 30 minutes or whatever, let's actually look at the first part of 2b. First thing, f of n is equal to 20,501. Okay. Let's simplify this in constants. This is just 1, right? We don't care about constants. We can just get rid of constants. So f of n equals 1 and g of n equals 1. So we're saying is f of n in O of g of n, right? So what we're going to do, let's just label this entire side the blue side and all these the red side. And when I plot them, I'm going to plot, and we can also label these green. I'll just plot them based off their colors, right? Okay, so now basically what I've done is I've put a blue L around the first column, a red one around the second column, and a green one around the third column so that I can describe each one of them individually and plot them out if I need to. And we've basically simplified this first one here down to 1 because we don't care about constants. Okay, so the first thing that I notice is that these are the same thing now, right? F of n and g of n are the same thing. Well, remember, when we have two functions that are the same thing, that's when we have a good candidate to put a tight bound instead of an upper bound or a lower bound. So this right here is actually going to be false because this should be an omega. It should be a tight bound. Just to say that again quickly, right? F of n is effectively, this is basically 1, and this is basically 1. So it is true to say that f of 1 is contained within theta of f of 1. Let's draw that out a little bit just to make it clearer. What does 1 look like? This is what it looks like for f of 1. What is, oh, that's a really close line. What does the other one look like? What does g of n look like? It looks like this one. These ones are the same line. They're both upper bounded and lower bounded by each other. So it makes the most sense to give a theta bound here. It's the tightest bound. Okay, the next one I think is actually going to be a little bit easier to understand because it's more in line with what we were just doing before. Okay, first thing first, we need to simplify these. So we want to remove any constants and we want to leave only the biggest term. What is the biggest term here? The biggest term is n squared. Why is it the biggest term? Because remember, as we plug values in, if we say, if we put n as 1, and we say, 1 to the second power plus 1, then 2 to the second power plus 2, plus 3 to the second power plus 3, et cetera, what we're going to see is that this n squared is always going to end up dominating over the original n, so it doesn't really matter as n goes to infinity. So this can simply be described as n squared. Similarly, we have a big constant here that doesn't actually mean anything. It doesn't matter how small the factor is of n to the third we're looking at. If we're looking at n to the third, it's going to grow at a rate of n to the third. Okay, so now basically what we're asking is we're saying, okay, we're looking at omega of g of n. G of n is n to the third, right? So if we want to look at omega g of n, let's draw n to the third, looks something like this, right? It's a very steep line. It's steeper than n squared. And it's an omega bound, so it's at or above this line, okay? So then the next thing is we're trying to say, okay, is f of n, is n squared basically contained within this? So if we draw n squared is not going to be as steep, right? And so we see the answer is wrong, right? Because we're asking, is this thing contained within this thing? And the blue thing is not contained within the green thing. How do we fix this? Well, I see here that the green line is shaded the wrong direction, right? So if it were shaded this way, it would make sense, right? Then it would be fair to say that, okay, the blue thing is contained completely within the green thing. That means that we should switch our notation. So this should not be omega of g of n. This should be O of g of n. So this is false. It should be O of g of n, right? And then the statement is true. Okay, continuing on. Let's simplify this. Okay, constant here, we don't need it. So we have 2 to the 2n. Then we have number here. This 4 to the n is going to grow bigger than n to the 100, right? So this is no longer needed. Okay, so now we're asking O of g of n. G of n is going to be really, really steep, because it's 4 to the n, which is a really, really steep function. It's O. So it's going to be everything at or below the line. Okay, and then the next one is going to be 2 to the 2n. So 2 to the 2n is going to be a smaller number than 4 to the n. So it's going to be maybe something like this, right? And so you might say, oh, sorry, mistake here. I'm dumb. It's not going to be a smaller bound, actually, because 2 to the 2n is actually just equal to 4 to the n, right? Because you have 2 to the 2, it's going to be equal to 4 times n. So that's 4n. My mistake right there. This is basically 4n. But everything we said so far basically holds. This is what we're describing. And so let's draw the blue line now. It's going to be exactly the same as the green line because it's the same. And so here's the question. Is this the most accurate statement we can make about the blue line and its relationship to the green line? And the answer is no. This is a true statement, I do want to note, because it is completely true that the blue line is completely contained within the region described by the green line. However, we could be more specific and we could put a theta bound, because if we put a theta bound, then we're not saying at or below the line, we're saying at the line, strictly at the line, which is the case if we look at this right here. Okay. Next one. So this one, we have log n to the 100. This interior doesn't really matter because log n to the 100 is the same as 100 log n. And this 100 is a constant, so it's just log n. And this one is n log n. Okay. So now what we're going to do is we're going to draw g of n again, which is n log n. It's going to look, I don't know, something like this, right? This is a theta bound, right? So there's no above or below, it's strictly on this line. And then if we draw log n, it's going to look something like this. And so we see, is this true? Does the green line describe the blue line? And the answer is clearly no, right? Okay. So then the question is, what could you change this to make this true? Well, we see that the blue line is completely below the green line. So if we were to shade down, we would contain the blue line within the green line. How do we shade down? Well, at or below is an omega. So if we change this from theta n to be, oops, sorry, that was the right one. If we change theta n to be O of g of n, then it would work, right? And that would make sense because we're saying log n is contained completely within the bigger thing. Okay, next one. We're getting there. Okay. N log n plus 3 to the n plus n. Which one's the biggest term here? It's 3 to the n. It's going to grow faster than any other term here. And then over here, similarly, which is the biggest term? N squared is going to grow faster than n, which is going to grow faster than log n. So we end up with something like this. Okay, let's plot it out. If we plot out the green, we're saying omega of g of n is n squared. That means we're going to draw an n squared. Oops, I know that all my lines kind of look the same, but you can imagine. It's going to look, we're going to draw an n squared. We're going to shade at and above. And then we have this n to the third, which is going to go even faster, right? It's going to be even steeper than n squared. And so the question is this relationship that we've established between the green and the blue line as descriptive as it could possibly be, as tight as it possibly be? And the answer here is actually yes, it is. This previous one was false. Let me mark it false. But this one is yes, it's true, right? We could give no tighter bound that would be true, right? At least strictly within the confines of this function, right? If these two lines were equal, then we could replace this omega with a theta bound, but they're not, right? So the best we can do to describe the two lines is this bound. So this is fine. Okay. Let's do the final one. N log n plus n squared. N log n is smaller than n squared, so n squared will dominate. Then we have log n plus n squared. N squared is bigger, so it's going to dominate. So then the question here is this true? You might be able to already tell it's true because we have the same thing here and here, and we're asking about a theta bound, but let's draw it out for fun. Okay, so if we have theta of g of n is n squared. So if I do like this, draw my n squared. Remember, no lines above or below because we're just looking strictly at a theta bound. And then we're asking, okay, we have this other line here. Is this the most descriptive statement we can make about these two lines? And the answer is yes, because they are the same line in this case. Okay, that's basically how you do all of those things. I know that was a huge informational load. And this is the kind of question that will take many days likely to process. So I would keep at it, keep trying it, draw pictures if you don't know what to do. And please go to office hours or ask your TA how to explain this, because TAs love explaining runtime. It's really fun. Once you get it, it's really fun at least. So yeah. Okay, 2C. Well, now that we got through 2B, let's look at 2C. So 2C is asking for the best case and the worst case runtime in terms of M and N. So this is a good place now to talk about the difference between best case, worst case, and omega, and theta. Okay, so we have these terms, O, theta, omega. We know this is an upper bound. We know this is a tight bound. And we know that this is a lower bound. Okay, great. Well, what's best case and worst case? A lot of people think that this refers to worst case and this refers to best case. That is not true. If you look online, you'll see first year computer science students the world over saying, oh, that's the worst case. That is not strictly true. O is purely mathematical notation, right? Remember, we're talking about at or below the line on an abstract graph. We're not talking about one specific case. We're not talking about best case. We're not talking about a worst case, right? We talked about best case and worst case. Now we're kind of leaving the realm of pure math and going into actual functions and saying, okay, we have a function. What's the longest it could possibly take? What is the least amount of time it could possibly take? It is true that these things are related though, because remember, if a function looks like this is an O of n, it means it's at or below this line, right? So if I ask you, what is the worst case of this function? The worst case is n, right? Because if this is the most time the function could possibly take, then that's the worst case. However, it is not fair to say that the worst case is O of n, because O of n doesn't just mean the most the function could possibly take. It means the most could take and any other amount of time as well, right? You could have a function that runs right around in here, and it would still be within O of n, but it's not a worst case, right? Anyways, try to be careful about those things. But let's actually look at this function and now try to address it in terms of best case and worst case. After we do this, I'll do a little bit more explanation about the bounds on them. Okay, so let's do this function here. And let's look at it quickly. We see it consists of two for loops. We want to look at how the for loops work and imagine the best case and the worst case scenario for them. So we have this little subroutine called ping. Ping takes constant time, returns an int, sure. And basically, let's look at what's happening in this loop. We have this double loop, and it says if ping returns some statement, returns true, we're going to break the loop. If not, we're going to keep going in this interior loop. Okay, so when we think best case, worst case, we want to think, okay, what is the case where we break immediately is the best case because we're not spending a lot of time. And the worst case is the case where we take the longest we possibly can, right? Meaning we iterate through this entire loop and never actually break. We never evaluate this statement to true. Let's look at the best case first. Okay, so in the best case, we're going to run this outer loop. This outer loop we can see is a linear time loop. Now, it's important to note that just because this loop says n, I greater than 0, I minus minus, just because this says linear doesn't mean the whole function's linear, doesn't even necessarily mean this loop is linear, because if there was a break somewhere within this loop, the best case would not be linear, it'd be constant. But that's a good place to start. We see that this loop runs in n, generally speaking. We look at this interior loop. Okay, how long does this interior loop take to run? It's the same thing, basically. It's going to take m. Notice that it's different in that it's going to start from 0 and go up to m instead of starting from n and going down to 0, but it's the same thing, right? This is, if you remember way back 10 years ago in this video when I was talking about iterating through all the elements in an array, this is basically like iterating through all the elements backwards. This is like iterating through them forwards. It takes the same amount of time. It doesn't really matter. So this takes n time, this takes m time, generally speaking. That does not necessarily mean that the runtime of those is just nm or n plus m or something. We also have to see what is actually going on within each individual function. So we see we have this if statement here, and this if statement, if it evaluates to true, will break the inner for loop, not the outer for loop, but only the inner for loop, right? So here's the best case, basically. We're running this outer for loop n times because there's nothing to break the outer for loop, so it's always going to run n times. Then we run this inner for loop one time, we get a true statement, and then we break out of the for loop, right? I'll say it again, basically. We run this outer for loop n times because there's nothing to break out early, so we're always going to run n times, right here. And then we run this inner for loop, we hit this if case immediately and break immediately, which means that in that particular case where we broke immediately, this loop does not run in m time. It runs in constant time, right? Because we just broke immediately. And you might say, oh, well, yeah, but that's only in the case that, you know, ping evaluates to something that's greater than 64. Yes, that's true, but remember, we're talking about the best case. We're talking about the case where we don't even care how probabilistically impractical this might be. We're talking the case where everything goes exactly our way and it is the minimum possible time it could possibly run, which is going to happen when ping breaks immediately. Okay, so in that case, it's just going to be in terms of n. The best case is going to be in terms of n, right? Because the m is just a constant. So it's going to be n plus some constant, or not m, sorry, plus like some constant like 1. We're going to get rid of that constant and we're going to end up with n. I'll talk about the bounds in a second. Now let's look at the worst case, basically. Okay, so again, this loop here is always going to run n times because again, there's nothing to break out of it early. So this is always going to give us at least an n runtime, right? What's the worst case though? Well, so if the best case is that we run this evaluate true and immediately break, then the worst case is that we run this evaluate false and then have to loop again, run this evaluate false, have to loop again, et cetera, et cetera. In other words, we never evaluate the statement. We go through the entire m loop without returning true on this ping, right? Okay, well, in that case, now this loop here, it does actually run m times, right? So this inner loop in the worst case takes m time to run. How many times do we run this inner loop? We run it n times, right? Because every time we run this once. If every run of this inner loop takes the full m time, we're going to end up with n times m time. Okay, great. So we've described the best and the worst case in terms of order of growth, but now it's time for us to actually apply some bounds to these functions. And my question to you is, what do you think the bounds are? Now, a lot of beginning students will make a common mistake, which is something I alluded to earlier. They'll say something like, okay, the best case is theta n, or is omega n, and the worst case is O of nm. This is not true. And let's think about it why. I don't even want to put it on my screen because this is such a horrible error. Okay, let's think about it by drawing it out again. Okay, let's draw the best case in blue. It's n, something like this. Let's draw the worst case in red. It's nm. It's going to be something that's increasing at a higher rate, right? It's some multiplicative thing, but it's not, you know, an exponential or a quadratic function or anything. But it's a steeper number. You might say, oh well, then why can't we just say theta? Why can't we just cross this out? And it's because it's not a constant, right? If this was a constant, they would grow at the same rate, but it's not, so they won't necessarily grow at the same rate. Okay, so now let's do the wrong thing. Okay, let's look at this. Let's say omega, and let's say O. What does that mean? Well, if we have omega n, that means at and above this shaded line, right? And if we have O of nm, it means everything down here. Okay, so logically thinking, we know that if the best case is n and the worst case is nm, then the function is going to run somewhere in between those two. It has to run at or better than the best by definition. It has to run at worst at the worst, right? That's what it means to be best and worst case. But look at the graph we've drawn. It not only describes this interior region, it also describes this huge region above and this infinitely large region below, which is not true necessarily. Or well, it's true at least, but just in the same way that 2b wasn't as tight as it possibly could be, it's not as tight as it possibly could be for us, basically, right? So whenever we're describing best and worst case, we're actually going to describe them in terms of theta. So why is that? Because again, you could say that the best case is O of n, but remember, or is omega n, but remember, omega just means at or above. You know, it's like if it's basically if I went to a restaurant, right, and you asked about it and you said, oh, how much does it cost to eat at that restaurant? And I told you, oh, at least $10. That could mean that it costs $10 to eat at the restaurant. It could cost $100 to eat at the restaurant. It could cost $1 million to eat at the restaurant. Those are all true statements. I just told you it costs at least $10. So, but if you ask me, what is the best you could get out of there with, what is the least you could possibly spend, I would tell you $10, right? It's possible. If you ask me, what is the best you spend, I could also say, well, at least $10, which is technically true, but it's like, why wouldn't you just say something that's more accurate, that's more concise, that's a tighter bound? Another thing to think about, another reason that best case and worst case are pretty much always going to be described in terms of theta notation is you can think of it this way. So the best case is when everything is as fast as it could possibly be, right? So if you come up with a situation that runs any slower than the best case, it's by definition no longer the best case, right? If you come up with a definition that's faster than the best case, well, then that's the best case. And the thing we were looking at as the best case is not the best case, right? In other words, you can't get better than the best case. And if you're any worse than the best case, you're by definition not the best case, meaning that there's only one runtime the best case could possibly run at, which is why it's theta, right? It's upper bounded and lower bounded by the same thing. Same thing goes for the worst case. I understand this might be a little bit confusing just to say, but I'll say it again anyways. The worst case is the longest it could possibly take to run, right? So why is it theta? Theta means that it always takes exactly that long, upper bounded and lower bounded by the same thing. Because if it runs any faster than this, than nn, it is by definition no longer the worst case, and it can't run any worse than this because we specified nn is the worst it could possibly run. Therefore, it will always run in nm in the best case and the worst case. Okay, so what does that mean? That means that overall, this function you could describe as taking theta n and O of nm time. However, the best case is always going to be when you hit this n, and the worst case is always going to be when you hit this nm, right? Why do we say best and worst case? Why do we do it separately? Because remember, omega just means at or above the line, so it's equally valid to say that this function runs in omega 1 time, because that's still true, and it's equally valid that to say that this function runs in, nm factorial time, because that's, at or below the line. But it's not the most descriptive, not the most accurate thing you can possibly say, even though it is technically true. That's why we have these best and worst case. And they're described in theta notation because they are always going to be upper bounded and lower bounded by the same thing. Okay, that's basically everything in this problem. I know this problem is a huge, huge, huge conceptual workload. I'd honestly recommend that you come back and maybe watch this video again at the final when you have so much more asymptotics under your belt, and then maybe it will make more sense in case it didn't right now. But that is how you do this entire problem. I'm just realizing there's actually more to this problem, but I'm going to do it in a separate video because I've taken too long here. So thank you for watching.